Hey everyone, welcome back. This week we talk about structural equation modeling, uh, which really we introduced sort of secretly last week when we talked about confirmatory factor analysis, which is a related method and under the larger umbrella of structural equation modeling. So, a few notes on this. I always like a good analogy, and you may not be familiar with this movie. In fact, you probably aren't. Probably not a great example. But there's this really great movie called The Big Lebowski. And one of the underlying themes of this movie is this guy called the Dude, who you see in this picture here. The Dude has his rug stolen, and it happens very earlier in the movie, and he spends most of the rest of the movie trying to figure out who stole his rug. And the Dude really loves his rug, and his main motivation for that is that it really ties the room together. And this is like a joke in the movie that the rug really ties the room together. It's very funny. You should check it out. It's a great movie. And what I like to think about for structural equation modeling is SEM really does the same thing. SEM is a framework of statistical approaches. It's really a framework that ties a bunch of different statistical methods together. So actually, a lot of the stuff we've been learning kind of individually as we've went along this semester can all be implemented in an SEM framework. And in some ways, there actually are some very unique advantages to doing so. So we have covered topics such as regular old regression, which I've called ordinary least squares regression, or linear regression that uses sums of squares. This can be very easily accomplished using SEM. And the difference is primarily how we obtain our model estimates. In SEM, we use something called maximum likelihood, which we actually learned about going all the way back to when we talked about missing data and when we talked about logistic regression, which also uses maximum likelihood. Confirmatory factor analysis, you'll recognize too from last week, also uses this concept of maximum likelihood to obtain model estimates. So that's a big difference. But really, everything we've covered so far, regression-based approaches, can be implemented in an SEM framework with the advantage of being able to incorporate what are called latent variables, which we've learned about last week specifically when we talked about CFA, but also the week before when we talked more generally about factor analysis. So the first phase of this, we're just going to get a little bit more familiar with the notation of SEM diagrams. And these are called path diagrams or path models. These are the bread and butter of structural equation modeling. The cool thing about all SEM models is that they can be written down as a picture. And that is a real advantage because a lot of times when we think about something like regression, it feels really abstract. And so trying to think about, okay, what is going on? What is the DV? What is the IV? How does this all fit together? That's actually relatively straightforward when you put it in an SEM framework. So let's start simple. Let's start with a basic Pearson product moment correlation, a correlation analysis that we'd use with continuous variables. So a little bit about path notation. Path notation has a few rules. One of them is that variables that are encased with a square are what are called observed, and variables that are encased with a circle are what are called latent. So you have observed variables and latent variables. Observed variables are the variables from your actual data set. So they are represented by a variable, a measure that someone has a score on in your data set. So here we have a relationship between a variable that measures depression and a variable that measures anxiety. And then we also have this curve going across here. And in path notation, a curved arrow is a covariance, which when standardized is equivalent roughly to a correlation. So if we wanted to show a correlation between these two observed variables, we would have both of those shown there and then a curve connecting the two, which indicates that we're looking at the covariance or the correlation between those two. And you can see the score there, which is 0.5. That is the value of the correlation coefficient between depression and anxiety. So if this is a standardized solution, and we learned about standardized solutions last week for CFA, if we ask for standard, I think it's ESTAT standardized, or no, SEM, stand or standardized, that will give you essentially the equivalent of Pearson's R to show the correlation between two variables. Okay, so let's kick it up just a little bit further. Let's talk about linear regression. We've actually seen most of these components before. In this case, a single-headed arrow like this, that's straight and not curved, is called a path. And a path is essentially a regression coefficient. It is demonstrating a relationship between two variables that's equivalent to what we would see in a regression. So in this example, the IV on the left side here is depression, and the DV is our outcome, which is anxiety. And what this is essentially a simple linear regression with depression, changes in depression, predicting changes in anxiety in a sample. Whoop, let me pop back for a second. So in this case, again, to repeat, we have the IV depression pointing towards the outcome, which in this case is anxiety. So another word for this in SEM type language, independent variables are exogenous, very fancy word. All this means is that there are no arrows pointing towards an exogenous variable. An exogenous variable is never an outcome in a model. The DV is what's known as an endogenous variable, which means there is somewhere in the model an arrow pointing to it. So it is an outcome of, at least in some phase of this model. And here again we have 0.5 on the line on this path, and that is telling us that that is essentially the simple regression coefficient for the relationship between depression and anxiety. So if this were standardized, a 1 unit increase in depression would predict an increase of 0.5 standard deviation units in anxiety. So that is a good old linear regression, simple linear regression, again represented in path analysis or path notation. Okay, a few other things to pay attention to that are going to end up being pretty important. And that is to pay attention to the variances and the residual variances that also exist in a model. So if a variable is exogenous, we also are estimating the variance of that variable. And it's typically indicated by a little curved arrow somewhere around the square itself. And if a variable is endogenous, we are calculating a residual variance as a parameter. So again, notated by this sort of curved arrow around the outside. That, in this case, would be what we think of as the error term when we think about a regular regression. So depression, predicting anxiety. Everything that is not predicted by anxiety is in turn estimated, and it's estimated as a residual variance. That's the error term. So in many ways, the error term in a linear regression is itself a latent variable. Crazy. We'll get there in a little bit, but that's essentially the idea. So the key thing for us to keep in mind is that even if not indicated, every time we see a square in a path diagram, we are typically estimating either a variance of that variable, if it's an IV, or a residual variance, if it's a DV. So again, we typically won't see this, but it's useful to remember when we're figuring out whether we can actually estimate models that we'd like to. Okay, so let's kick it up again one more time. So here we have a multiple regression. Here we have anxiety, again, as our outcome, our endogenous variable, and it is being it is being treated as the outcome. And then we have three variables that are IVs, independent variables, predictors that are predicting anxiety. We have a perfectionism score, we have a depression score, and we have an SES score. And what you'll see is each one of these predictors has an arrow pointing to anxiety, and we have a number, an estimate on each path right here. So this is equivalent to the regression coefficients for each three of those predictors on the outcome. So the regression coefficient for perfectionism, is 0.3, depression's 0.26, and SES is minus 0.11. Now, a couple other small things to notice about this. Notice over here, now this is a multiple linear regression. We also have some curved arrows over here on the left side that are connecting all of our exogenous variables, all our predictors. This over here, remember when you run regression, we always talk about the idea of statistical control. So the impact of perfectionism on anxiety after controlling for all other predictors. This is a really cool visual, and this is one reason why I love path analysis. This is showing you what we actually mean statistically when we talk about control. So we are controlling for the relationship between all three of these variables by estimating covariances, sort of like correlations between them. And so here's the relationship between perfectionism and depression, perfectionism and SES, and depression and SES. And if we were to add more predictors, we would get more of those individual correlations. And that is what happens when we control statistically for all other predictors. That is the control portion, which actually is going on under the hood. You don't always see this. You don't actually, if I were to run a regression in Stata, for example, and say reg or regress and a bunch of variables, I often don't get the covariances between the variables. But we actually do get that when we use path analysis or SEM, because SEM is very specific about all the relationships between all the variables. The last thing to point out is this bold 0.25 up here. And typically in path analysis, this is equivalent to the R² value for this DV, which is anxiety. So what this is saying is everything that is predicting anxiety right now is explaining about 25% of the total variability in anxiety, just like we would interpret a regular R² value. Okay, so we just covered correlation and simple linear regression, and now multiple linear regression. Whew, that was fast, right? In about 10 minutes, we breezed through a big chunk of statistical learning. And believe it or not, SEM enables us to go even farther. For example, we can examine interaction effects. So here we have another multiple linear regression. In this case, depression is our dependent variable. And we have three IVs. We have perfectionism, stress, and the interaction between perfectionism and stress, which is simply the product of those two variables multiplied together. So this is exactly the way we would specify this in a regular regression. In a regular regression, we would use the pound sign or the hash sign, and we would connect two variables that we wanted to test in a moderator analysis. So in this particular model, we could look at, is stress a moderator of the relationship between perfectionism and depression, or is perfectionism a moderator between the relationship between stress and depression? Remember, statistically, those two are equivalent. A statistical model does not distinguish between a moderator and an independent variable. That's our job as the researchers who know the theory to understand which really is a moderator and which is an IV. But that's essentially the same relationship, and again we have this connection of all the different observed variables, the covariances between all those observed variables, and that gets us statistical control, which then in turn gives us a traditional regression model. So again, a moderator model is very possible in this framework. So now we're going to talk a little bit about mediation, which we talked about all the way back early on in the class. Mediation is actually really easy to implement in a path analysis or SEM framework, because mediation really lends itself to sort of a visual representation that actually shows what's going on. So basically what happens is when you do mediation, you capture the mediated model all in one single analysis. So what you have here, so here is the relationship between perfectionism and depression, and we have a mediator, which is conflict. So we're testing, does perfectionism change your level of conflict, which in turn impacts your level of depression, and then of course what is the direct effect between perfectionism and depression. Oops. So this is actually estimated all at once in a single regression model, where we are estimating an A path, and that is perfectionism predicting conflict. We're estimating a B path, which is conflict predicting depression, and a C path, which is perfectionism predicting depression. So simultaneously in SEM, you can estimate a model like this, which is really, really cool. Now, usually you would use something called bootstrapping to estimate this, and that we will get into next week when we talk about advanced SEM applications. Mediator analysis or mediation analysis is one of the main ones that we talk about. So we'll hold off on that for a minute. But this is really, I wanted to show you just how kind of elegant and simple it is to represent a mediation model like this in SEM and estimate it without a ton of trouble. You can also do things that are a bit simpler. For example, you can even estimate a t-test, an independent samples t-test in SEM framework. So here, it's a very simple relationship. Remember, a t-test tells you if there are group differences in a situation where you only have two groups, right? When you have a treatment or control, for example. And in this case, we have an outcome, anxiety, and we have a dummy variable, which indicates whether or not someone received a particular treatment. And so this variable is equal to 1 if someone received a treatment, or 0 if they receive the control. And when you estimate a model like this in SEM, the value that you get for the intercept is actually, or the constant, is actually the average score for your control group. The value for the slope plus the intercept is the value for treatment. Or another way to think about that, the value for the slope is the difference between treatment and control. And then the p-value tells you whether or not those means are different. So you can actually implement an independent samples t-test in this same kind of framework just by using a dummy variable and an outcome and then a single path. You can even get a little fancier and implement an ANOVA, a one-way ANOVA. So here's an example where we have folks who were assigned to one of two treatments and a control group, and we want to know if our treatment made an impact on anxiety. And so the one trick is we have to dummy out our original categorical variable that showed the different treatment groups. So let's say our original variable looked like this. People who had control group got a 1, treatment 1 got a 2, and treatment 2 got a 3. We then need to just create two dummy variables that indicate membership in one of those two treatment conditions. So treatment 1 up here, that's equal to 1 if someone received treatment 1, and it's equal to 0 if they were assigned somewhere else. Treatment 2 is equal to 1 if folks receive treatment 2, and 0 if they receive something else. And the reference category, which we've left out, is the control group. So that is going to be the value that we get from our constant or our intercept, which is pretty cool. So similar to the t-test, you can get means for each group. And this, if I coded it this way, I will get estimates. So I'm going to get an estimate here, which is the difference between treatment and control, and an estimate here, which is the difference between treatment 2 and control. I should say up here is treatment 1 and control. And so this kind of dummy coding would compare all treatments to the control group. But if you move control up here, then you can get comparisons between a specific treatment and control as well. So it's super flexible and able to provide you with lots of different ways of representing these statistical models.